Lesson 3 for the SE3 assignment on parts per million and parts per billion in solution equilibrium. Has anyone ever heard of ppm or ppb? I assume your answer is yes. And what does it stand for? Well, I'm not sure if you'd get this. Not everyone will, but I'm sure there's some people who will say ppm means parts per million and that ppb means parts per billion. But what does it mean? If something is, okay, let's say my water is 5 parts per million fluoride, that means out of a million things in my water, there would be 5 of those million things that would be fluoride. Things like of a million molecules, maybe 5 would be fluoride ions, or maybe out of a million atoms, 5 in the sample are fluoride, or maybe if I had 1,000,000 pounds of water, 5 pounds would be fluoride. Okay, I don't know. Good thing we're doing this lesson because now I'm curious. So weak concentrations are often expressed as ppm or ppb since the general public finds this easier to understand than molarity, or at least they're more comfortable with the term parts per million and parts per billion than they are with molarity, because everybody has heard the term parts and per and million before, and they've all heard the word billion before. But when we start using words that people don't know, like molarity, they get uncomfortable. So even though it's not as accurate, and we'll find that out later in the lesson, and that most people are happy saying ppm or ppb, even though they don't know what it means, they're happy using it. Now this is a water analysis from Lumsden in 2016. We can see that in Lumsden water, we have an arsenic content of 1.3 micrograms per every liter of water. In barium, we've got 5.4 micrograms per liter, and cadmium we have just under 0.56 micrograms per liter, and so on and so forth. Look at lead. We even have lead in our water, 0.60 micrograms per liter, and uranium, 3.1 micrograms per liter. So that's what we find inside of Lumsden water. But how does this micrograms per liter and nitrates 2.5 milligrams per liter, how does that all relate to what we're talking about today? So to understand what parts per million and parts per billion mean, we have to know that a liter of water weighs 1 kilogram at 4 degrees Celsius. And when we're talking parts per million, that is the number of milligrams solute divided by liters of solution, because 1 milligram is 1/1,000,000th of a kilogram. Parts per billion is the number of micrograms solute divided by liter of solution, because a microgram is 1/1000,000th of a kilogram. Since parts per million and parts per billion are not scientific expressions, they do not carry a unit. So these are the two formulas that you will want to add to your formula sheet. The parts per million equals milligrams divided by liters, and parts per billion equals micrograms divided by liters. Pause and put these on your formula sheet. So why don't chemists use parts per million and parts per billion? Because like if we had a water sample and it said the solution is 16 parts per million chloride and 16 parts per million bromide, well, that would mean their concentrations are equal, right? Or are they? Or would there be more chloride than bromide if they're both 16 parts per million? Or would there be more bromide than chloride? Now we said that parts per million equals milligrams divided by liters. And we said we had 16 parts per million chloride, 16 parts per million bromide. So that means we've got 16 milligrams of chloride and 16 milligrams of bromide in a 1 kilogram sample of water. So there is the same weight of bromide and chloride dissolved in the water. But if we look at the periodic table, we see chloride weighs half of what bromide weighs. So that means if there is an equal mass of each, there must be twice as much chloride as there is bromide ions floating around in solution. How many parts per million is a solution if there are 2.4 grams of Ki in 1,500 milliliters of water? So parts per million equals milligrams divided by liters. Since I've been given grams, I will have to convert grams into milligrams. So big brackets, grams, Ki on the bottom, so that grams Ki and grams Ki can factor out. And we're going to convert grams to milligrams. 1 milli equals 10 to the negative 3. I run it through my calculator and I have 2,400 milligrams of potassium iodide. I'm dividing by liters, but I have been given milliliters. So I will also have to convert from milliliters to liters. So big brackets, milliliters on the bottom so they can factor out, and I will convert milliliters to liters. And 1 milli equals 10 to the negative 3. I run it through my calculator, and the total volume is 1.5 liters. So I will substitute these numbers into my equation, punch it into my calculator, and I get 1,600 parts per million potassium iodide. Example 2. How many parts per billion is a solution if there are 0.00024 moles kBr in 50.0 liters? Parts per billion equals micrograms divided by liters. So I will have to convert moles into micrograms. I will start by converting moles, well, big brackets, moles on the bottom. I'm going to convert that to grams. If I look on my periodic table, I find that 1 mole weighs 119.0023 grams. Moles and moles will factor out. I ran through my calculator, and that gives me 0.028561,657 grams of kBr, which I will then convert into micrograms. So big brackets, grams on the bottom, micrograms on top, and 1 microgram equals 10 to the negative 6. I run that through my calculator, and I have 28,561.657 micrograms of kBr. And that will go in my numerator, and I'm dividing that by 50.0 liters. Run that through my calculator, and I get 571.21104, corrected to 2 significant figures, means the solution is 570 parts per billion kBr. How many moles of chromium-2 ion are in a 2-liter solution that is 225 parts per million chromium-2 ion? Well, it says parts per million, so the first thing I write is parts per million equals milligrams divided by liters. If I'm looking for moles, well, I can get moles if I find grams, and I can find grams if I isolate milligrams. So to get milligrams by itself, I will multiply both sides by liters. On the right-hand side, the liters will factor out, and milligrams then equals liters multiplied by parts per million. I will substitute in 2 for liters and 225 for parts per million, and when I punch that into my calculator, I wind up with 450 milligrams of chromium-2 ion. Now I will convert milligrams to grams. So 450 milligrams, big brackets, milligrams on the bottom, grams on the top, and 1 milli equals 10 to the negative 3. Milligrams and milligrams factor out, and I have 0.45 grams of chromium-2 ion. Now to convert from grams to moles. 0.450 grams chromium-2 ion, big brackets, grams on the bottom, moles on top. But what am I going to put into my bracket? Because chromium weighs 51.9961 grams per mole. But I've got chromium-2 ion, which means it has lost 2 electrons. While chromium has 24 protons, and it has, on average, 28 neutrons, and it has lost 2 electrons that weigh 1/2000th of any one of those protons or neutrons. So the amount lost, because it has a positive charge, is negligible. So we're going to use the mass directly found on the periodic table. So 1 mole of chromium weighs 51.9961 grams. Grams and grams factor out, run it through our calculator, and we wind up with 0.00865 moles chromium-2 ion. And that's the end of the lesson. You're good to move on to the assignment.